Welcome everyone to our first webinar. My name is Rob, I'm the CEO of DigitalCNC, and I'm joined today by Rich Bonnell and Emily Pickford from the AMRC. Let me just share my screen. Can you see that okay?
Yep, we can.
Okay, amazing. So this is the first webinar of 4. It's our very first one, so if things don't go quite right, please be gentle. And so the webinar today is just an introduction to advanced CAM, virtual machining, and also an introduction to digital CNC for precision machining. So like I said, my name's Rob. I was AMRC until very recently, where I spun out the company, and I'm now CEO. And I've had the pleasure of working with Emily and Rich for many years in the machining group and the cutting tech team, who have been supportive of this software. So they have the privilege of being in the very first webinar. So Emily, Rich, do you want to just give yourselves a quick introduction about just your background and your experience in machining, and also maybe just what you're doing on the day-to-day at the AMRC in the machining group?
So I'm Emily Pickford. I'm Technical Fellow for Subtractive Processes within the machining group at AMRC. So I've been with AMRC 9 years now. We tend to focus sort of mid-TRL scale process level research, so doing more fundamental and feature-based testing, looking into CAM developments, virtual machining, digital tools, on everything for milling, drilling, turning, and grinding.
Great, thanks, Emily.
Cool. Yeah, my name's Rich Bonnell, Innovation Fellow at AMRC, working the same subtractive process team as Emily. Been at the AMRC for a total of 11 years now. Background is apprentice-trained machinist, worked at various different engineering companies, multiple different sectors, and ended up at the AMRC, I say, in the subtractive process team, helping support mid-TRL research.
Amazing, great. Thanks very much, guys. So, as I mentioned today, this is webinar series, part 1 of 4. This first one was to be an intro to virtual machining. It's very light touch, and then as we progress through, then we're going to go into far more depth into specific areas. So the next one we'll look at, dynamic milling for aerostructures, which is a particular strength that we have at the AMRC. After Christmas, we'll come back and we'll look at 5-axis machining, and then we'll also look at some of the ultra large defense forgings as well, because funny enough, they have similar challenges. Not necessarily because of the tolerances, but because of the acceleration in some of these ginormous machine tools. Please register for the full series at digitalcnc.ai/webinars. Quick little bit of housekeeping. So this session will be recorded and will be emailed to you the link within 24 hours. Well, please use the Q&A panel for questions, and hopefully this should be 35 minutes plus 10 minutes for Q&A. Fingers crossed. Okay, so what we're going to do today, really the theme of today is to understand, does your machine do what you think it's going to do? And ideally, that's what we want to know before we start cutting any metal. And that's why we have virtual machining solutions. So what we'll cover, we'll look at what does the traditional workflow look right now for many manufacturers? What's the pressures that are driving industry? What are those drivers? Emily and Rich will support us with some toolpath fundamentals of what they do day to day in the cutting tech team. We'll look at that critical gap of actually what is the difference between what we're seeing in CAM and what we're seeing in the real world. What are those digital tools to support us? We'll give a demo of the Digital CNC toolbox software, and then also we'll have a Q&A at the end with all 3 of us. So without further ado then, this is an incredibly simple slide of what traditional workflow has been for many years. So this CAD, CAM, CNC. So I've just divided it into 2 colors to start off with. So on the left hand side, you can see I've highlighted in yellow, so what's the digital side of things. So when we change anything here in the digital side, ideally it's it's free. We know it's not costing us anything. On the right hand side, in the green there, this is the physical area. So when we want to change something or do anything in here, this is time on machine, this is time inspections, and this is any iterative stuff we do here that we're not cutting production parts. Effectively, this is costing us time, this is costing us money as well. So you can see we go from the CAD model through to CAM, and we take the experience of the CAM engineer, and we do parameter selection, toolpath strategy, etc. We'll post that, okay, so it's a machine specific G code then on the machine, then we'll listen to it, we'll look and see the fields. A lot of experience here, could be on machine edits, back through that inspections, and then finally, after many iterations, might be on the way to making production parts as well. I mean, Rich, is this kind of what you've been familiar with most of your career before you came to the AMRC?
Yeah, it relies a lot on the intuition of either the manufacturing engineer or the machinist, or depending on how individual companies work and structure how they design the processes to get on machine. But the vast majority of it comes from prior experience and having done it before. There's obviously a skills gap, shortage. People are retiring, people move into different careers, and that experience goes, and it takes a long time to replace that and to learn again. And then there's all the different nuances around different machine tools, different controllers, new materials, etc. That just needs that experience and that time to be able to fully get a good process on machine. Anything that can help speed that up or benefit, that's really, really useful.
Yeah, good. Thanks, Rich. Emily, what do you see the drawbacks of doing this method are?
Well, as Rich has just mentioned, there's a big issue with the skills gap. The engineers that we're getting coming through now haven't got that level of experience. We don't train people in the same way. They're needing to have different skills, especially with using digital tools. Which is exactly why we're pushing towards using these digital tools, using digital twins and virtual machining, and using methods to capture the knowledge from that generation and make it accessible without needing decades to work on the shop floor.
Yeah, definitely. I mean, so something we'll look at in the coming slides as well, but we've got an aging workforce, we haven't got people coming to fill the gaps, we need to upskill people quicker. But really, when we've got the PlayStation generation, or probably generation after the PlayStation generation, this should be something that kind of people want to use digital tools, want to do things faster, want to use AI and machine learning and put them onto the shop floor as well. So yeah, cool. So just moving forward a bit, just want to talk a bit about some industry drivers. And so there's some key changes which are happening across the aerospace and defense community. Big changes for me include things like new products coming out. And so we can see here, on one of the pictures on the top left, we've got, the UltraFan, new gearboxes, which has got, difficult to machine materials. Therefore, we've got new manufacturing processes. We've got the certification requirements. We've got, the drive towards digital thread and this, what's the word? Digital product passports and things. Then we've got, our drive to zero defects to get things right first time. And, and right first time we know is absolutely critical, especially for, these, tier 1, tier 2 suppliers and these smaller SMEs that, if we start kind of, having wasted parts or damage, this is fundamentally critical to their bottom line as well. We can't be doing this. Sustainability requirements, we know these are coming in, the CSRD directive, from the EU, will mean that we'll have to do carbon reporting on our OEMs. Eventually that will feed through from, to our supply chain. It's not quite there yet, but we know a lot of them are getting ready for that. And like we said, probably the most important thing that we've, underpins it all, we've got this skill shortage. So, I mean, Rich, from the AMRC's perspective, where do you see these priorities coming from and these drivers?
I think zero defect machining is an interesting one, or just right first time in general. We see at the AMRC, even from a research perspective, where we used to get 3, 4, 5 test vehicles, as we call them, to develop the processes and iterate and improve and develop, eventually come up with a suitable process for a partner. We quite often now get one to get it right first time. So that really brings into focus the digital machining aspect of it, and as much preparation as we can do beforehand to get on machine, to de-risk, to optimize. There is gaps in allowing us to do that completely, which I think we'll talk about later. But yeah, we see that. So certainly as partners do as well. And the ability to get on machine and right first time's a massive one. And just to reiterate as well, I think the skills shortage is critical. I know we've talked about it previously, but that's the other one that really comes to the fore, and we see it at the AMRC as much as partners see it in their production facilities as well.
Yeah, interesting. Anything to add to that, Emily?
Yeah, definitely. You mentioned material, so and as Rich said, we're getting less and less test vehicles through, but in general, there's less material available. There's a drive towards more sustainable practices, so people aren't wanting to use as much material for new product development. We've got issues in the supply chain throughout multiple industries, so not able to get hold of material as easily. And with the drive towards sustainability, we're trying to reduce energy usage and increase carbon reporting and things like that. So using tools like digital passporting are really key towards achieving that. And as we've moved more towards a sustainable future, we're seeing more challenging materials, near-net parts with more complex shapes and that sort of thing. So it's how we actually support the development of the processes for these more complex features and materials coming through.
Yeah, excellent. I'm glad to actually go to my next slide, actually. So we're talking about things like, near-net shape. Obviously, additive is now moving into certain areas. How do we machine those? I mean, I'm not going to talk about composites, but that's, incredibly complex too, flexible toolware and things. So if we look at kind of into the kind of the fundamentals now, what's your bread and butter? How do these drivers affect the toolpath and the machining strategies that you're doing? So, we've got a few things on here talking about, machining strategy, obviously choice, CAM, parameters, which are key, this trade-off between part quality and productivity, which is sometimes not an inverse relationship. It's a really difficult multi-objective optimization problem, but where, we need to have part conformance, but yet we also need productivity and make it faster as well. So just in terms of your day-to-day and what you're seeing, Rich, just talk me through a bit about kind of how you approach some of these and really why they're important.
Yeah, I mean, machine choice is just working through the process of how we go around a theoretical project, which we need to decide the machine that we're going to produce the components on. Kinematics plays a key part in that. If we can achieve the dynamics of what we're asking for the process to develop, so the machine choice is really, really important. CAM strategy is becoming more and more crucial. I think it's pretty well acknowledged now that for HRSA type materials, dynamic milling strategies can be massively beneficial. There is then a blurring of the lines into aluminium machining. There's a compromise or a distinction to be made around the part geometries and the length to diameter ratios of the cutting tools as to when dynamic milling strategies come into play for aluminium machining. Which is something that we spend quite a lot of time on. So that's a key factor. CAM quality is also a key part of it. The control of the radial immersion into the tool into the workpiece and force leveling and the overall quality of the CAM that we see is a major consideration. Once we've got that, once we're happy with that part of the process, we're then into tool selection and parameter selection, and again understanding the kinematics of the process and as much as we can do desktop based wise before we get onto machine. So particularly if you're talking about special tools with long lead times, we can't be on machine we can't wait until we're on machine to decide when what the optimum tool geometry is going to be. We need to have that information beforehand. And then also, one of my favourite sayings is everything in machining is a compromise. So everything's played off against another thing. Or, you know, obviously, if you take productivity, there's a compromise to add productivity between surface roughness, tool life, part accuracy, tool center point accuracy. It's all a compromise, and it's understanding that relationship between the parameters that you've got the power to adjust and what the trade-off to that is going to be, and anything that we can do prior to getting on machine to understand that compromise and that trade-off's really important.
Yeah, absolutely. What about you, Emily? What kind of, in terms of these, you know, where do you focus most of your efforts in your day-to-day?
Yeah, I mean, throughout this, you'll see that my background is a bit more in the virtual world. But using the digital tools to prepare for machining trials before you validate on machine, and to aid in decision making and predict what's going to happen ahead of time to try and drive towards that right first time. So we use virtual machining a lot and different digital tools, but they've all got gaps. Each of the softwares have got gaps, such as when you look at machining dynamics, machining kinematics, material variations, looking at sort of tool model accuracy or even tool wear when you're on machine. It's being able to account for these things, and then specifically around kinematics and tolerance settings. Obviously, DigitalCNC can help bridge that gap. But it allows us to crucially assess achievable parameters in more complex toolpaths. So we can maintain good radial immersion and get good chip control from a CAM package, but that's assuming that you're maintaining your feed rate, so which can be challenging. So when you've got inconsistent parameters and you're slowing down in corners and things like that, it's not allowing you to accurately plan in terms of time and quotations as well. So using tools like this, it's really powerful for us.
Yeah, good. Sorry, go on, Emily.
I was just going to say, and partners as well, not just.
Yeah, without a doubt. And so the key thing, you know, in your world, you know, you're trying to do as much in the virtual space as possible. So that way the machines are doing what they should be doing, which is making production parts. You know, you can't be wasting time, you know, trying to iterate on the machine itself and trying to say, oh, let's do 50 of these different, you know, strategies, when actually you could do it in the virtual space, and maybe you just do 2 strategies in the real world. So you know, we can't eliminate you know, prove outs, you know, but we can reduce them, you know, and before we get there, we can take this many solutions and bring it down to, you know, to this many solutions, and hopefully we get somewhere closer to where that point is. So, you know, we're not too far from where the, you know, our optimized or our, you know, our ideal scenario is for our machine parameters, our selection, and everything else. And that's the whole point with all these different tools. And there's an awful lot, you know, around there. So let's just kind of look at the next kind of thing, where this is the kind of critical gap, and this is where, you know, a lot of my research has been over many years. And, you know, we know that there's a gap between CAM and the real world. We know this, and we're trying to drive that. But it's, you know, CAM is still absolutely crucial to what we're doing. And, you know, the reason we have this is because, you know, the machines have got their own kinematics. You know, this is the accelerations, the jerk settings. You know, this is how they behave when you're roughing is different to finishing, for example. You know, we know this. Different configurations, you know, 5-axis compared to 3-axis, AC, you know, kind of configurations compared to, you know, swivel heads. Toolpath geometry is, God, I mean, it's so complex, you know, in tool geometry, just and how we're laying them up, and the impact it has on the actual machine kinematics and the behavior of the machine. You know, the machining tolerance, you know, this is that C-toll that we put in the header information. You know, the difference between machining something at 10 microns and 50 microns could be 100% in cycle time difference, could be doubled, depending on what we're doing, you know, and the toolpath type. Smoothing type is another big one. And within that, you know, the interpolation type, which, you know, and I know this is very nerdy stuff, which I get into, but there is a fundamental difference in the mathematics behind an 840D controller and a Cinumeric one, you know, and Heidenhain. And so when all of a sudden you had, you know, a look ahead of 10 in the 840D or 20 in the 840D, and then the new ones, you've got a look ahead of 5,000, it's not a little improvement, it's fundamental difference in how we compute these things. And that has a massive impact on actually the behavior of the toolpath and how it moves, not just in the feed rate, but also in terms of that TCP position, where it's going to do, where your maximum errors are going to be because of your blending errors, etc., and things like that. That ultimately has an impact on your, your chip load, and everything else, falls from that. Likewise, cam tolerance. I think a lot of us, Rich, I'm sure, back in the day, the difference between having a really finely discretized toolpath and a wider one. And if you put it through one that's got, an old controller, you're going to get that buffer filled, and you're going to have, problems which might not be from geometry or machine tool kinematics, but it's actually from computation, and it's getting stuck, and it can't come through. So there's an awful lot, which goes into this, but that has a massive effect. So we know that, because of that, we don't reach the feed rates, cycle times are elongated, and our TCP position, is not often where we think it might be. So when we're setting our machine parameters and we're setting that feed per tooth, for a certain, optimum condition, we know we're not reaching that. So actually, we don't know what we're actually machining at. We haven't got that confidence in our process. If we haven't got the confidence in our feed per tooth, then our cutter workpiece engagements are off. Then our cutting forces are not accurate. So, feeding into all our optimization. So whether you're doing any of the numerous software packages out there that are optimizing based on force profiling and force leveling, well, actually, if your feed rate's wrong, then your cutting force is not accurate. So, we've got some optimization problems. That can then lead into, non-conformance in part geometry, etc. Because we know that we're off in terms of our tool bending as well. And likewise, we're going to have longer cycle times, and that's going to lead to poor planning and quoting and everything else which falls from that. So this is fascinating. This is just from, this is just from machine kinematics. This is just from tolerance settings that you are selecting yourselves. And if you get these wrong, this has massive impact on the process. So I put like a little important stamp here for the bottom. So, machining parameters, if you get selecting the wrong parameters here, you might never reach them, for depending on certain toolpaths, so the toolpath itself, if we're not putting those cutter locations in the right place, then we can never achieve them. Machine selection, it's a massive one. Okay, we've got two machines, might be relatively simple. One might be able to do dynamic milling strategies, one can't, So no point, putting the wrong strategy on the wrong machine, or it might be double the amount of cycle time if you could do it. That's really important if you're doing a quoting a job. And as we know, header parameters have some of the biggest impact on cycle times that there are. And if you don't put them in correctly, or you forget to put them in, it will default to the tightest tolerance. And we see a lot of skills gap around this. Those who've been around for years, they know this, but some of the new apprentices coming through, they don't know what to check for. And if the post isn't automatically putting them in, then actually, you could be doing, effectively finishing tolerances on a roughing operation, which then you're doubling that cycle time as well. I mean, Rich, I know we spoke at, I don't know how many conversations over the past few years we've had about this, but just talk about kind of some of the things you've seen around this area of the header information.
Yeah, I think probably worth just quickly going over where we've come in the discovery of the importance of kinematics. I think, to be perfectly honest, it was during COVID, I think, because I remember there being a skeleton staff in the workshop, and we were running a machining trial on the EcoSpeed aluminium machining platform. We'd got some stability issues. We did some investigation into it. The conclusion of that was to reduce the tooth load of the process. So from memory, we were going from 120 microns chip thickness down to 80 microns. That was a recommendation. We'd got a cycle time for the process that we were doing currently. Before we ran it in material, we ran it in air just to make sure everything was okay with the updates. We noticed that the cycle time was exactly the same. So even though we'd reduced the feed rate by a third, the cycle time was the same, because the machine tool wasn't achieving the original feed rate, and it couldn't even achieve the slowed down feed rate. And that's when we first seriously started looking at the issue. That machine tool we were capable to get data out of the machine tool in terms of TCP positions, but that was at the time, that was the only way that we could get that information, by running it on machine, capturing the data through the ADAS system, analysing it, and then going back on. There was no way of simulating that sat at a desktop PC. And that's when we really started to understand the importance of the kinematics. Then we got into the, like say, the header settings for cycle 832 and CTOL, etc. And that's when it really became clear that it was a critical part, especially in high dynamic processes. The other thing I'd add to that as well is there's definitely been this shift towards more dynamic milling strategies, controlling that radial immersion, even with aluminium aerostructural machining, and it becomes more important as we move towards more of these complex these toolpaths. If you've got a simplistic straight line cutting toolpath, yes, you're going to get slowed down in the corners, but the vast majority of the toolpath is going to be at the achieved feed rate if you've got anything like a capable machine tool. But in terms of dynamic milling, where you've got constant changes in axes movements, it becomes super critical. Add on to that 5-axis processors, depending on the part geometry. If you've got a large radius, large diameter component, it's not necessarily the linear feed rates that become your restricting, become the limiting factor on the process. It can be your rotary axes, and they can have a much poorer kinematic performance, and you can get drastic reductions in between what you're asking for and what you're getting in terms of tool center point feed rate. Then you've got your tolerance in, and it's there's and we've seen huge differences in cycle time just based on the header information. And again, it's a compromise. Open your tolerance up, you get a poorer TCP tolerance position area, but you can get a much faster cycle time. But it's about making that informed choice between the two and being able to do it whilst you're sat at your desktop in your cam, not to go on machine and then analyze data afterwards.
Definitely. Good. Just moving on for time. So I know Neil could be here for 2 hours if we wanted to chat about this stuff. So I'm going to move forward on to kind of what kind of tools are available to us. And Emily, this is more in your wheelhouse now. So Emily, I know you spent, the good, best part of 8-9 years kind of benchmarking these tools and have got close relationships with a lot of these companies. So you know quite a lot of them. On the left-hand side, I've just put a list of kind of common, CAM and CAD packages that we work with, across the board. And then going down diagonally, I've kind of tried to put a bit of a, where almost through the process a little bit here. With some of the CAM automation at the top left, and then moving down to, on machine, high-speed recording in the mirror. So Emily, join us quickly, just talk us through some of the key softwares here. And then on the next slide, I've actually put a slide on where it looks like in the digital toolbox in terms of the workflow. So we can use both slides to explain some of this.
So we use majority of the software packages on there at AMRC. So one of the unique benefits of AMRC is that we have got access to a wide range of different software. So we're not just limited to one CAD package, one virtual machining package, etc. So we do generally use Siemens NX, CATIA, Hypermill, as well as some of the others for CAM generation. Verification software, we use CG Tech, Vericut for collision detection, looking at G-code verification, and then force simulation, using software such as Third Wave, production module, CG Tech, Vericut Force, as well as like MacPro, productive machines, and that sort of thing for predicting cutting forces, and also using that to develop your CAM strategy to analyze the quality of the toolpath that's coming out of some of the CAM packages. We can do more macro-based simulations using sort of Third Wave Systems Advantage to look at tool geometry analysis, temperature, stress strain simulations, and chip formation as well. So really looking down into the science of the cut, as well as some AMRC internally developed simulation models as well. So
Yeah.
each one of those has a strength, but they can't do everything. So they all are all individually powerful, but when you bring them together and start using them to complement each other, that's when you see the real benefits and they become much more powerful tools. So for example, very cut, it's brilliant at collision detection. You can do force simulation. Same with third wave, we can look at the material science and the cutting force models and things.
Yeah.
CAM gives us the toolpaths, but then there's always a bit of a gap. So I've mentioned before, machining dynamics, kinematics, as Richard just discussed and yourselves just discussed at length, looking at the tolerance settings and the headers and things like that, incorporating toolware. These packages can't do everything. So obviously DigitalCNC fills one of these gaps. So it's the only software that we can get controller accurate feed rate prediction. So making the force prediction from that and TCP error is much more accurate. So it takes away a level of that error. If you bring that together with some other software such as Productive Machines or the MAL softwares as well for chatter prediction, that again makes it even more powerful. We're just starting to look into the more AI CAM generation tools and process planning and things. And then crucially, taking the data from what we get on machine and feeding that back into the process as well. So the main focus for us at AMRC is using all these tools. How can they work together to really drive that process planning and aid decision making ahead of time? And how can we make it better for next time as well?
Yeah, for sure. I mean, I know, for years we've been, taking high-speed data from the machine tools, using that to validate our models. Classical models and now these days, the more AI machine learning based models, much like Lambda function and toolpath and CloudNC you're looking at, and likewise Gemini is, taking that high speed data, but you need to be connected to the machine, don't you? So straight away, so there's a barrier to entry already with some of these softwares. What we're trying to do is say, what can we do ahead of time without even touching, the actual machine itself? So I appreciate this is a bit of a messy slide, but I was trying to kind of put together what's available and who's doing what. So again, on the left-hand side in the yellow, you can see I've put the digital products in there. So again, this is free, we can change things. It's not costing us any money in this space. And then the right-hand side is our physical, where this is costing us money, and time and machine time, and if we're not cutting production parts, we're wasting time and wasting cash here. So just really briefly, Emily, just quickly talk to me, maybe a minute about kind of how you see some of these softwares feeding into what you do in CAM and your parameter selection, toolpath strategy, and how that works.
Yeah, so the integration piece is really important. So generate the CAM strategy, the CAM toolpath in whatever package you're using. Having the simulation tools such as DigitalCNC, third wave systems that have the plugins to fit into the CAM package is really important, because then you're not opening another piece of software, creating another material file, another tool model, and then going through it all again iteratively. We can use the plugin for DigitalCNC, we've got an accurate feed rate, we've got an accurate TCP error, we know exactly what's going to happen on machine. We can run that through a virtual machining software such as third wave systems or very cut force to get an achievable or see what the actual forces are going to be, see what the actual chip load is going to be based on the feed rate. And then make the iterations there. So it's still quite a manual process, but you can go back into CAM, change your toolpath slightly, change your parameters to see what you can actually achieve before going on machine. Then post it all out again, run through very cut, check that you're not going to have any collisions. You can use other tools such as Productive Machines to check for chatter if you're doing aluminium machining and that sort of thing. And then actually go on machine. There's obviously still a level of validation. They're not perfect systems by any means. So we still need to get on machine. We still need that person stood there listening and feeling but
Yeah.
taking some of the onus out of that and aiding the decision making ahead of time. Like you say, instead of having this many choices to make or this many different parameters, we can narrow it down to sort of this many. So that's really how it fits into our process at the minute.
Yeah, exactly. Yeah, good. And then, I mean, we've been talking to a lot of machine tool suppliers and also, tooling suppliers who are creating, these days, because of the skill shortages, they tend to be creating a lot of turnkey solutions where they're giving the full package, to these SMEs or to these companies and the tier one suppliers. And, with software like this, and that we're seeing in the yellow space here, they could do most of this in the virtual space. So when they're doing their costing and their quoting and they're trying to do things, they don't need to be on the machine to do this. And actually, we find, those who are making turnkey solutions can, be doing time trials in the digital space to give them accurate, production times and things ready for their, for their customers and for their quoting. So, we can do all this offline and not on a machine. What I'm going to do now is I'm just going to bring in just a bit of a demo that we had at the AMRC a few weeks ago when we did the AMRC showcase, which was the 2-year event that we hold at the AMRC, the machining group, with all the major aerospace partners. And I'm just going to relatively quickly go through this because I'm very aware of time. I knew we'd overrun. So obviously here what you can see is CATIA, and this is just a really simple example that I want to show here, just to really highlight a really unique, a simple use case. So here we're seeing an aerostructure part. This was aluminium, and this was done on the Echo Speed, so one of the biggest machines we've got at the AMRC. And you can see here we've got a nice dynamic toolpath. Now, running this through CATIA, in the bottom right, you can just about see it says 19.4 seconds, roughly there. And we know that that's probably going to be relatively inaccurate. Now, when we ran this on the machine, I think it was 36.6 seconds on the Echo Speed that we ran on the day. So, but actually, you wouldn't want to iterate on the machine, would you? Because the Echo Speed is about £3 million, and you want to be cutting chips all the time. I know companies like GKN, are using this to make the wing spars of the A350, I think, and so they want to be turning 24 hours a day. You don't want this off. So what you can see here is that we've just clicked on DigitalCNC and it's pulled all the parts and the programs through into the main page. And what we're going to do is we can just click on the load the single toolpath on here. So now we can bring a toolpath through from here, click on the left-hand side. We can click on the machine. So here we click on the Echo Speed. We can click on the machining type. And so right now, finishing, roughing, that header information again. And then we can pick on machining tolerance here. So that's that CTOL or the cycle 832 setting. And so we can decide what do we want to run this at. And, we're roughing, so we're going to pick some like 100 microns, as standard. And then we press run toolpath analysis, in less than a second, we're going to do that instantaneous analysis of what does that toolpath look like. I'll just pause it there. So you can see in the top right, in the toolpath metrics, it's predicting 36.8 seconds. It's almost exactly what the Echo Speed is. Because we're using a generic controller here. We're trying to predict the behavior of multiple machines and get, close as we can. But the CAM cycle time is about 20. So you can see this red bar, it's not hitting the feed rate for the majority of the time. So that really should give the operator, an understanding to go back into CAM and change the parameters that we're doing, because you're not going to be hitting the feed rates and you're not getting the feed per tooth. And then your cutting forces are not what you think they are. The optimization is not what you think it is. And this, it all feeds back into it. And instantaneously, you can see that here. We can then click on, the cycle time optimization, and here we can see what happens if we change the tolerance. This actually is the first time anyone in the world has ever shown this. We know that has a massive impact, but let's go back and show that again a little bit. But usually it's finger in the air, or we double the NX time, or we check the very cut time and add 50% depending on it. But now we've got it exact, and we can see that, which certainly is great for upskilling and certainly training some of the new engineers coming through. We can have a look at our toolpath. We can see areas that we can highlight, and we go back into there. And also we can have our feed rate analysis. And we can zoom in here. We can start doing some real detailed things and figure out what's going on and go back into CAM, and we can change that. But this is not not connected to the machine. This is purely prior to machining, and giving you all that information so you can go and make some decisions. Now we can also do some analysis on this. So you can see in this bit we are we can Left-hand side, we've got our standard parameters we've pulled through. On the right-hand side here, you know, we can choose the machine, we can change the toolpath if we want, so we can compare toolpaths against each other, different strategies, which is really important. We can even compare, you know, the cycles and on machining tolerance. In this example, we're just going to do tolerance here. And so again, you know, we'll run toolpath analysis, calculates it immediately, and we can see the difference here. Look at that difference there. We can even put ROI calculators in here, have many parts, and we can see here, just by changing the tolerance, you know, on this amount of parts, it'd be about £14,000 difference. So if you get the tolerance wrong, this has financial implications, you know, and now we've got quantitative metrics which states this, which is great. So we've got data for the first time about relating this stuff. We can even create, you know, reports. I think here, we're just changing the machine on this one. What happens if I change this process to a different machine? You know, the C52 is pretty good compared to the echo speed, so there won't be too much difference here. Again, 36.8, 33.9 seconds. What does it look like in terms of that, you know, cost difference? £2,000 if we change that machine, you know. And again, we can create some reports here as well. So, you know, if we want to be doing continuous improvement, you know, actually, you know, we can get some data, give it back to our managers and go back and say, look, we should change this. It's going to save us this amount of money if we go back and change these parameters, you know, of any of these fixed processes. This is really handy because, you know, for the first time, you know, we're giving documentation back to say, this change means this amount of money, which is really cool. But actually what we might be more interested in is, you know, the whole part. So on this little demonstration here, we brought everything through. You know, we're going to kind of select a different machine to move it to a different process. And this could be the case that we were thinking about a capital investment decision. You know, here we can have a look, number of parts, run the full session analysis, and straight away what we can see is, you know, if we were to change from one machine to a different machine, then it's going to save us approximately, in this case, 10,000, you know, £11,000, you know, in that process. It could be the fact that, you know, you are doing a quote. It could be, you know, you're quoting, and actually by the time you're quoting, you win the work, but when the work comes in, your machine is no longer available, you've got to put an older machine, it's going to take twice as long. So actually when you're quoting, you should probably want to quote on the older machine, you know, so you haven't got it. And again, here, this final bit, you know, we can pull out, you know, various different reports and stuff, you know, based on that and feed that back into the reporting chain. I'll just stop there because that was really quick. A quick way of demonstrating some of the software as well. We're a bit short of time, so you know, it avoids expensive testing for iteration. You know, we can look at areas to optimize. You know, we can do accurate, you know, time studies and planning, and ultimately it feeds into that capital investment decisions as well. So I appreciate that was a bit of a whistle-stop tour, and we probably need to have you know, another 6 webinars to go through all this stuff. So what I would ask though, guys, is just, you know, what were your kind of takeaways from that and your takeaways from some of these discussions, just so we can wrap up a little bit?
For me, I think the key one in terms of the software is the integration into the CAM. So yeah, I'm saying this in the very early days of DigitalCNC to you, Rob, it's got to be able to integrate into existing processes if you want the uptake to be as high as possible. If it's another piece of software that needs another setup session doing to start getting that information out, it's going to hinder the uptake. The fact that it's sat in CAM and it integrates in, it's pulling all through all the necessary information is key. And the other one, the other point I just want to make as well is if you're not considering cycle 832s and CTOL tolerances as well, the thing to bear in mind is that majority of machine tools will defer to conservative tight tolerances that will massively restrict the productivity of the platform. And it's up to you as an ME or as a machinist, as a planner to make sure that you're using the correct machine setting tolerances and CAM tolerances to get a productive process.
Yeah, thanks, Rich. Emily?
Yeah, I think one of the more powerful tools that you've got in the software is I think it was from probably discussions between yourself and Rich as well to show that compromise between your TCP error and your cycle time and your achieved feed rate. And as Rich has said before, it's always compromise when you're machining. But then also the cost based on your machine and your tolerance settings and things like that. You can see how that's a really powerful tool for OEMs that are trying to increase rate and maybe create sort of a business decisions and to support those decisions, but also for SMEs as well, and how it supports their more accurate quotations and to help them win work and again make decisions on a smaller scale.
Yeah, brilliant. Thanks, Emily. Yeah, I think for me, kind of my biggest key takeaways really is one that, you know, your CAM doesn't understand machine behavior, you know, and so that's why you're seeing these, you know, ginormous differences in feed rates and certain toolpath machine combinations. You know, virtual testing, you know, is there to close that gap between, you know, CAM and the real world, and hopefully, you know, it's possible, you know, it's free to do this in the digital space, you know, compared to the expensive physical space. And the key thing really is you know, these tools, they're not, you know, they're all complementary. Each one's doing a different thing, each one trying to solve a different problem and trying to work together to try to minimize that piece. And, you know, DigitalCNC is one of those tools that complements the existing toolbox. And it's important to understand the strengths and the weaknesses of each of them and how they can work together to hopefully reduce costs, you know, accelerate that time to market and reduce the amount of physical trials required for a new part introduction, hopefully. So I appreciate we've ran over a little bit. So just to sum up, you know, the recording link will be sent out within 24 hours with a copy of the slides. If you want to try and access the software, please get in touch with us at info@digitalcnc.ai. The next webinar will be on the dynamic mill for aerostructures, where I'll try to get a bit more nerdy into some of the, maybe not the mathematics, but show a few more figures and some details about kind of why things are slowing down in some of these corners. And please sign up for them on digitalcnc.ai/webinars. And finally, just thanks guys, and we'll hang around now for some Q&A. So